at one more. An elevated cistern problem. We've got a water cistern that's elevated 15 meters above the ground, and it feeds a pipe that terminates horizontally 5 meters above the ground as shown. With what velocity will the water leave the pipe, and how far from the end of the pipe will the water strike the ground? Well, the first thing I'm going to do is try and come up with a strategy here. I think I can use Bernoulli's principle to find the velocity of the water right here at what we'll call point 2, and then it becomes a projectile problem as to where it's going to land. If we call this our point 1, we've got a height of 15 meters here and a height of 5 meters here. To find the velocity, why don't I just bring this back, and if I call point 2 ground level for the first part of the problem, for figuring out the velocity, then the height here will be 10 meters, because that's the difference. So let's apply Bernoulli's equation and see how this is all going to look and work out. Bernoulli's equation, P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. All right, as we look at that, some simplifications we can make. P1 is open to atmosphere. P2 is open to atmosphere. They'll have the same pressure. We can subtract those out of both sides. V1 is going to be roughly 0. We can make that go away. On the right-hand side, if we're calling this the 0 height level for the first part of our problem, setting that as our 0 and the height here is 10, we can make that term go away. So we've simplified Bernoulli's equation to say that rho GY1 equals 1/2 rho V2 squared. Or, as we substitute in our values, first off, we can get rid of the rho's. GY1 equals 1/2 V2 squared, or V2 squared equals 2GY1, or V2 equals the square root of 2GY1. Notice how similar that looks. V equals square root of 2GH, the conservation of energy value we found in order to determine how fast something's moving after it's been dropped some distance. V equals square root 2GH by kinematics or by conservation of energy approach. Same idea. So V2 will be equal to the square root of 2 times G, 10 meters per second squared, times Y1, 10 meters, or square root of 200, that's about 14.1 meters per second. So our water is going to be leaving the pipe down here with the horizontal velocity of 14.1 meters per second. Now we've got ourselves a projectile problem where we've got a height of 5 meters and we need to find the horizontal distance the water travels. All right, well, let's first figure out how long that water is going to be in the air. That's a vertical kinematics problem where V initial vertically is 0, delta Y will be 5 meters, acceleration will be 10 meters per second squared, and we need to find the time. I would use the equation delta Y equals V initial t plus 1/2 AT squared. But again, V initial is 0, so that term goes away. T then becomes 2 delta Y over A square root, or 2 times 5 over 10 square root, or 1 second. Now I can use my horizontal kinematics to figure out how far it goes. Horizontally, the velocity is going to be a constant, 14.1 meters per second. It's going to be in the air 1 second, so delta x is just going to be velocity times time, 14.1 times 1, or 14.1 meters. Putting a couple of these concepts together in order to get a big picture solution. All right, hopefully that gets you a great start with Bernoulli's principle and Bernoulli's equation. Thanks for watching. Make it a great